So today we are going to do space-time diagrams. This is the last topic under A5 relativity. So what is a space-time diagram? It's basically a pictorial representation of all the relativistic phenomena that we have learned so far. And this is introduced by one of Einstein's friend, H. Minkowski, and this is why it is also called as Minkowski diagrams. So just for your information, that there are a lot of space-time diagrams introduced by many scientists and physicists, but in this chapter, we're only focusing on Minkowski diagrams. So in this diagram, basically, we're going to plot time on vertical axis, whereas position on horizontal axis, which is quite opposite to what we have done under the chapter A1, A2, and A3. So one thing to be noted down that instead of directly time, we're going to take CT, which is basically a time axis with a factor of speed of light, which gives the unit meter, and x-axis basically position in meters. Now, yes, and if you have a doubt why CT on y-axis instead of just time period on y-axis, very soon I'm going to reveal that understanding that why CT instead of T. But yes, so let's understand the term called word line. What is meant by the term word line? So take an example. There's a tree and there's a person standing at a distance d from the tree and he's stationary, he's not moving. So if I have to draw a line or basically graph, so basically I have to draw the points, right? Or data points. So this is the first data point. Basically the position is at d when time t is 0. So CT will also be 0. And then after 1 second or 1 unit time, CT1, that this is the coordinate, and then this, then this, then this. Basically, what is happening here? You can see as time is passing on, his position is not changing because the object is at rest. And if I draw a line through all these coordinates, we call this line as a world line. Now, how the world line be for an object moving at a constant speed? So this is going to be the coordinate, and if he's moving at constant speed, the position will keep on changing at the same amount of distance for the same amount of time. And when I'm going to join all this line, it is going to be a world line again, but for a moving object, which is moving at a constant speed. Now, we're going to look at a mathematical part of this world line. Basically, what does slope represent? What does angle represent? Everything else. So slope is basically change in y by change in x, which is going to give you the ratio of speed of light in vacuum to the speed of light to the speed with which that object is moving. The v in this formula is the speed with which that object is moving. Now, since we know the theta here, we'll see what theta can help us with. So I'm going to use the trigonometric ratios tan theta, which is opposite by adjacent. So opposite is your change in x and adjacent is your change in y. So that gives you v over c. And this formula is very, very important. Very soon you'll get to know. Now, we'll see a word line for a photon, basically any electromagnetic wave. So say this is a light bulb which emits out a photon that moves with the speed of light in vacuum, V is equal to C. And by using the formula, theta is equal to tan inverse of V by C, we'll get theta to be 45 degrees. That means the word line for photon is going to be a very smooth line making an angle 45 degrees with both x-axis and y-axis, right? Now, let's also understand why we have chosen CT on y-axis instead of just T. Now, because of the formula derivation, if you look at it, because the change in y is ct, we end up getting the ratio as v over c. If the change in y wasn't ct, we would have got this ratio as x over t. And that x over t would not give us the ratio as v over c. And if the ratio would not be v over c, then we may not get the ratio to be 1 at any point of time, which will never give us angle to be 45 degrees. So this possible world line for photon is possible. I mean, the reason we have got a world line for photon to be at an angle 45 degrees because the ratio over here ends up getting 1. And this ratio can only be 1 when V is substituted as C and CC being cancelled out. And C is only when introduced in this formula when the y-axis was labeled as CT instead of just T. That's it. Next. So we're going to see what are the possible and impossible world lines we have. According to the formula, since theta is equal to tan inverse of V by C, when V is equal to C, this is going to be the photon world line. But because no object in the universe can travel with the speed greater than the speed of the light, that means theta can never be greater than 45 degrees. That means this is the possible region. And this is the only region where all the possible world line can exist. And this is the region where no world line can exist. That means this is a possible world line. The green one over here is a possible world line, and the red world line is impossible because it is making an angle greater than 45 degrees, means it is representing V is greater than C, and that is impossible. Now we're going to see different world lines. So this is your a photon which is going to the right, and this is a photon going to the left. So please note that not always we're going to draw the world line to the right, which can also be represented to the left. Left world lines means the particles or the object is moving to the left. So photon world line onto the left means photon is going to the left. Similarly, particle, this line is representing a particle going to the right, whereas this one particle is going to the left. And finally, the red one is the world line, which is impossible because it is making an angle more than 45 degrees. And that means the speed is greater than c, which is not possible. Next. So I'm going to assume as an event, basically an event where bomb is ignited at time t, where the bomb was at a position x, and that event is going to be ct comma x. What is an event basically? So event is basically a coordinate that consists of time and spatial coordinates. So time is basically t time period t, whereas spatial coordinates means position of x, y, and z. But in this unit, we are going to ignore y and z coordinates because we're going to deal with the problems only one dimensional, means object or particles, everything moving in a one dimensional axis, but not in three-dimensional space. But yes, with the knowledge of one dimensional, you can apply into the three-dimensional because it is going to be a similar way of calculating or understanding the space-time graph. So yes, so I'm going to draw a world line of photon, which is 45-degree lines on both sides. That is one to the right of our object, and one is going to be the left of our object. So this is going to be the future of E1. What do you mean by future of E1? That means if the bomb blast. So one of the particle of the bomb can fly, and the next event E2, I'm going to talk about any event of a particle, of object or a particle that has come out of the bomb due to the explosion can be anywhere in this region in future, right? And what was the past event means what could have led to this event E1, which is what is event E1? Is a bomb ignited at this time. And the past of E1 means maybe someone bringing the matchstick at this moment of time, someone is finding the matchstick at this moment of time to ignite the bomb. So anything in the past to reach this event E1 can be in this region, and anything in the future after the bomb explodes can be in this region. But whereas this region and this region is impossible region because it is making an angle greater than 45 degrees. That, I mean, if I put any event over here, I mean, I'm assuming that event is a connected event to E1. That's wrong because I'm saying that the particle from E1 has flew away from this point with a speed greater than the speed of light, which is not true. But yes, I'm not saying that no event can exist in this region. I mean, E4 event can exist in this region, but in that case, you have to make a note that E1 and E4 are independent events. They are not connected events. That means, for another example, that E5 is an event, E5 and even in E4, all three are independent events. They are not connected events. But whereas E1, E3, and say E6, E1, E3, and E6. These are these can be connected events or may not be. So I'm not talking about 100% sure they are connected events, but they are possible. There is a possibility that E1, E3, and E6 are connected. E6 was an event in the past to reach E1, and E3 is the future of the event E1. Now, let's talk about how is going to be the world line for photon for different frame of references? But wait, what do you mean by different frame of references? So one, obviously we have drawn a stationary frame of reference, say Earth, and say a rocket is moving away from us. So what is going to be a frame of reference for that? So I'm going to have to draw another axis, x-axis and y-axis for the rocket, as similar as x-axis and y-axis for the Earth. But so keeping both of them together will make them overlap and will not make us understand which axis we are looking at. So that is why we're going to squeeze the prime axis, which is the axis for rocket, with some angle theta here. We'll talk about this theta further, but let's talk about how is the world line photon going to be with respect to any frame of reference. So take an example, there is a bus moving and there's a photon emitted out of that light of the bus. So what is the speed with which the photon is moving? It is moving with the speed of light with respect to the person, not just person, but with respect to the bus as well. So what I'm trying to say is that the with speed of any object changes with respect to different frames of references. That is what we have learned under Einstein uh, relativity. But the only object in the universe, the only thing in the universe whose speed doesn't change for different frames is the speed of light. And therefore, the world line will be passing with an angle 45 degrees, no matter whether it is with respect to uh, Earth axis, or with respect to rocket axis, or with respect to spaceship axis. It's the same thing. Now, let's focus more about this different frame of references. So I'm going to separate them, right? So we know mathematically this is how you locate any coordinate. I mean, if I talk about this event E1, you know how far it has run on x-axis and how much rise it has on y-axis to locate this event E1. Pretty simple. But for this axis, which is ct prime and x prime, we're going to follow the same logic, but the only difference is it is a squeezed version of it, right? That means we're going to draw same parallel lines to my y-axis and parallel lines to my x-axis. Now keep in mind that 1 unit over here is not the same 1 unit over here. So that means we're going to use some transformation to find how much is 1 unit on our normal S frame axis equivalent to 1 unit on S prime axis, which we'll look into it later. Next, there's some interesting facts. Let's take an example. There is an event E1 and there's an event E2. You understand that event E1 happened at this time and event E2 happened at this time. So that means they're not happening at the same time. Obviously, they also have not happened at the same space, but they happen at the same time with respect to S prime axis. Means any event in space that you are observing two stars, they both emitted light at different amount of time for you, and they're different position with respect to you, but they both might be emitting the light at the same time with respect to an observer who is moving with the right amount of speed. But wait, sir, how do I know the speed with which that observer is moving? So that observer axis is what we have drawn with the squeezed version here. The theta is the angle which help us to know the speed with which this moving observer is moving. Because we have already learned the formula, the tan theta is equal to V over C. And the same formula will be helping us here to find the speed with which the moving observer is moving. Next, look at this one. So E3, E4, definitely not happening at the same time, also not happening at the same position. So imagine there are two stars, has emitted the light at two different positions, P1, P2, at two different time period, T1, T2. But with respect to some other observer, which is moving with the right amount of velocity, by knowing the value theta, you can find the velocity of that observer. They can see these two events, E3 and E4, happening at the same position. That's interesting, right? I mean, the two stars with respect to you on Earth are not at the same position. They are two different positions. Maybe they're separated by a distance of 1 light year or 2 light years or 3 light years. They're separated by some distance, but there might be someone in the outer space moving in a spacecraft with the right amount of velocity may see these two stars at the same position. Means they both are overlapping for him. Interesting, right? Anyways, moving on. So yeah, so for example, you have an event E whose coordinate with respect to S prime is 1, comma 1. What will be the coordinate for the same event with respect to the S frame, which is the rest frame? So I don't know, right? We can't just say 1 comma 1 for this because obviously they are not to the same, they both don't have the same scale. So use it as 1 comma 1 for this as well. So since they're unknown, let me call it as CT comma X. Now the point is, how do you find those coordinates? So step number one, you're going to find the gamma factor. And step number two, you're going to use your Lorentz transformation equations basically to get the value of X. You're going to use gamma times x prime plus vt prime. To get the value of ct, you're going to use gamma times ct prime plus vx prime by c. Next, length contraction. So say a ruler is at rest in S frame, as you can see in the picture here. Now, how do you find the length of this ruler on S prime frame, which is moving with speed close to the speed of light? But one thing we know that it will see a length shorter than the actual length due to the relativistic effect. Step number one, you're going to draw two world lines parallel to CT axis as shown in the figure. And then you'll find the point of intersection. As you can see, this is the first point of intersection, and that's the second point of intersection. And that will give you the length of the ruler in S prime frame. But make a note that maybe pictorially it appears that this length of the ruler is larger than this, but that's not true because the scale for both the frames are not same. Next, what if the ruler is at rest in S prime frame? In this case, you're going to find the length of the ruler on S frame by drawing two world lines parallel to CT prime axis as shown in the figure. And then you'll find the point of intersection that is this and this over here, which will give you the ruler length in S frame. Now, it is clearly understandable that the length of the ruler is shorter in S frame compared to S prime frame since the relativistic effect will cause the length contraction. Now, one thing to be noted down here that if the ruler is rest on S prime frame, you will draw those world lines parallel to your CT prime frame. In case the ruler is rest on S frame, then you're going to draw parallel lines or parallel world lines to the CT frame. Next, what about time dilation? For example, there is a clock at rest in S frame, and you're going to find the time on S prime frame. Now, because we have learned that length, if it is at rest on S frame, you draw parallel lines with respect to your X frame, but here that's not the case. You will draw parallel world lines to the opposite frame, means you're going to draw two world lines parallel to X prime frame. I repeat, the clock is at rest on S frame, but this time your world lines are going to be drawn parallel to your X prime frame. And then again, the process is same. You will look for the point of intersection that will give you time in S frame. Similarly, if the clock is at rest on S prime frame, and this time you're not going to draw parallel lines to your X prime frame. No, you will not draw parallel lines to your X prime frame. Instead, you will draw parallel lines to your X frame. And that point of intersection will give you the time in S frame. Next, simultaneity. For example, there are two events, E1 and E2, as shown in figure, and they're simultaneous. As you can see, the E1 and E2 happen at the same CT time period. That means they're simultaneous event with respect to your S frame, which is stationary frame. But are they simultaneous with respect to S prime frame? The answer is no. How do you do that? To locate these events on CT prime frame, you're going to draw parallel world lines to your X prime frame. I repeat, these two events are simultaneous with respect to your S frame, but they're not simultaneous with respect to your S prime frame. But how do you find that? So you're going to draw parallel lines to X prime frame to locate the coordinates on CT prime frame. Instead, if I have to locate these events, E1 and E2, on X prime frame, then you will draw parallel lines to your CT prime frame, right? That's it. Let's solve this problem. Use a space-time diagram to estimate the speed of frame S prime. So you know the value of theta. So I'm going to use the formula tan theta is equals to V over C. That implies V is equals to C times tan theta, which is equal to C times opposite 3 meters divided by adjacent 5 meters. And if you simplify this, you will get the answer as 0.606. Next question, find the scale on red axis. How do you do that? So first I'm going to assume the coordinate CT prime to be 1 meter, right? I'm going to consider a coordinate on CT prime to be 1 meter. Now I need to find out how much is this value on CT axis. That's first thing I'm going to do. But note point, because we are finding out how much is CT prime 1 meter on CT prime axis, at this condition, your X prime is going to be 0 because you're locating this coordinate, right? So on this y-axis, your x-axis values are always going to be 0. Simple math. Similarly, when I'm going to locate x prime as 1 meter, when I'm going to locate x prime equals 1 meter, to find the value of x, in this moment of time, my CT prime will be 0. Now, let's start. How do you find out CT? So I'm going to use our Lorentz transformation equation, that is CT is equals to gamma times CT prime plus Vx prime over C. Now, how do you find the value of gamma? By knowing the value of velocity, which is basically by knowing the value of theta. So let's do that first. So tan theta, which is opposite by V over C. So from this V is equal to C tan theta, which is C times 1.5 meter divided by adjacent is 2 meter. That gives me the velocity as 0.75 meters per second. Sorry, 0.75 C. That's the velocity. Next, gamma, which is equal to 1 over root over 1 minus v square over c square. By substituting the value of v square, which is 0.75 square, it gives us a value of gamma as 1.5. So keeping this value of gamma and substituting here 1.5 times ct prime. What is ct prime? 1. And what is the value of x prime when ct prime is 1? I clearly said x prime is going to be 0. That means ct is 1.5. So at x prime 1, at ct prime 1, I'm sorry, at ct prime 1, my value of ct is going to be 1.5. That's what the value says here. Done. Now similarly we'll do for x1 prime. So x will be again using Lorentz transformation, which is going to be gamma times x prime plus vt prime. So again gamma is 1.5 and x prime is 1, and I clearly said ct prime is 0, so therefore this value will be 0, which is equal to 1.5 meter again. So that means when a value of x prime is 1 meter, at that moment of time, a value of x is 1 meter, 1.5 meter. Now let's do some past paper questions. The diagram shows the axis of coordinate system S at rest relative to the Earth. Earth is at origin of S. X prime and ct prime are the coordinates of reference frame S prime in which spacecraft is at rest. When the origins of these two sets of axes coincide, all clocks in the frame show 0. So the speed of spacecraft is 0.80 c as measured in s. It's asking you what is the speed with which the spacecraft is moving. So since this frame ct prime and x prime is off the spacecraft, and the angle theta subtended over here can help us to find the speed with which this spacecraft is moving. So what is the formula? So we know that tan theta is equals to v over c. V will be c times tan theta. By plugging the value of tan theta, what is tan theta? It's opposite. This is your opposite, which is 4 light year, divided by adjacent, which is 5 light year. You will get the answer as 0.80 c. Next, an event has coordinate x is equal to 0, and ct is this with respect to S frame. Show using Lorentz transformation that the time coordinate of this event in S prime is ct prime. Now I'm going to use this Lorentz transformation, which is given as ct prime is equal to gamma times ct minus vx over c. The value of x is 0. That makes ct prime equals gamma times ct. The value of ct is given as 0.60 light year, but what's the value of gamma? So we'll calculate the value of gamma separately. The formula for gamma is 1 over root over of 1 minus v square over c square. That is 1 over 1 minus, what is the value of v, which is the speed with which the spacecraft is moving. That is 0.80 square c square over c square. And if you simplify this, the value of gamma will be 1.67. I'm going to substitute the value of gamma here, which is 1.67 times the value of ct, 0.60 light year. That will give me 1.00 light year. Next, label on the diagram with letter P the point on ct prime axis whose ct coordinate is 1 light year. Okay. So since we calculated CT prime coordinate as 1 light year, they're asking you to label that point P onto the CT prime axis. I mean, you can't just randomly say this as 1 light year, right? You have to accurately locate it. So how do you do this? Before that, I just want to touch a small fundamentals in math. For example, if this is how our x-axis and y-axis are, and there is an event E here, which has the coordinate x comma y. If I ask you locate this event E on x-axis, you will draw a line parallel to y-axis. If I ask you locate this event E on y-axis, you will draw a line parallel to x-axis, right? So using the same logic, since we know that 1 light year on CT prime is 0.60 light year on our rest frame. So this is your 0.60 light year on your rest frame, and you have to locate this coordinate on CT prime. So since I'm locating this coordinate on CT prime, I will, which is your y-axis for S prime, you will draw a line parallel to your x-axis of S prime and see where that line intersects the CT prime. So let's do it. I'm going to draw a line parallel to my x prime. As you can see, that line is parallel to my x prime, and this is where it intersects, and that is my point P. Basically, the coordinate 1.00 light year. Next, at CT equals 0, a light beam is sent from Earth to space station at rest, 4 light years away in S. Basically, space station is 4 light years away with respect to the rest frame S. Event R is the arrival of light beam at space station. Draw lines to indicate R on the diagram. So first of all, I'm going to draw a world line for the light. So which is at an angle 45 degrees with both x-axis and y-axis. Next, I'm going to draw a vertical line, drop a vertical line from 4 light years onto this light world line, photon world line, and that's going to be my event R. That's going to be my event R. Next, determine using the diagram or otherwise the space coordinate x prime of event R in S prime. So they're asking you what is the coordinate of x prime? Means since the coordinate of R on x is 4 light year, what is the coordinate on x prime axis for the same event R? Now, since we wanted the coordinate on my x-axis, I will draw a line parallel to my y-axis. So look at this. I'm drawing a line parallel to my y-axis and see where it intersects. That's the point where it intersects, right? And that's going to be my, let me label it as R prime. Fine. Or maybe you can also use a Lorentz transformation to locate this coordinate. So what is the Lorentz transformation equation? X prime is equals to gamma times x minus vt. The value of gamma, which was calculated previously as 1.67, and x is 4 light year, minus speed with which it is moving, the spacecraft is moving, is 0.80 c times value of t is 4 light year. And if you, wait, don't forget, this value of v is 0.80 c, but the t is 4 light years divided by c, because this CT value is 4 light year, but we wanted the value of t there, which is 4 light year divided by c. And this c gets cancelled. And if you simplify this, the value of x prime is 1.33 light year. The space-time diagram shows this Earth frame with a word line of a spaceship S moving away from Earth, CT prime 0 when CT is 0. That means the origin of both moving frame and stationary frame overlaps at time 0. First question, determine the speed of the spaceship relative to the Earth. So we can use the value of theta here to determine the value of speed, which is tan theta is equals to V over C. That implies V is equals to C times tan theta. And what is tan theta? It is opposite, which is, let me consider this length, which is 4.2 kilometers divided by adjacent. That's the adjacent, which is 7 kilometer. And if you simplify this, the value will be 0.6c. 0.6c. Next, a flash of light sent by an Earth observer at CT equals 2 kilometers is directed towards a spaceship. So you can see that the light is sent when time is 2 kilometer, right? This from here, the light is sent towards a spaceship. Estimate using space-time diagram the time in seconds when the flash of light reaches the spaceship according to the Earth observer. So first of all, whenever a photon is sent out, the first thing that you want to do is, without even thinking further, is draw a world line for the photon, which is at an angle 45 degrees. So I'm going to take a ruler here, set the angle to 45 degrees, and from CT equals 2 kilometers, I'm going to draw a world line at an angle 45 degrees, which is going to be a world line of a photon. So that's my world line of a photon. Yeah, next. So as you can see, the world line intersects the spacecraft at this point. So that's the point where photon reaches. So this is the point where photon left the Earth, and this is the point where photon reaches the spacecraft. Now, the question was estimate using space-time diagram the time in seconds when the flash of lights reaches the spaceship according to the Earth observer. So from this, we can identify that a CT is about 5 kilometers from the Earth axis, right? That's about 5 kilometers as per the Earth axis. So T will be 5 kilometer divided by C, right? So plug in the value of C, which is 3 times 10 to the power of 8, will give us the value of time period in seconds. That's 1.7 times 10 to the power of minus 5 seconds. Next. Determine the time coordinate CT prime when the flash of light reaches the spaceship according to an observer at rest in the spaceship. So basically they're asking you what is the time coordinate CT prime with respect to the moving frame. So I'm going to use the Lorentz transformation equation, that is CT prime equals gamma times CT minus Vx over C. So since we have already calculated the value of gamma above, which was okay, we have not calculated, so we have to calculate separately, which is going to be 1 divided by 1 minus v square over c square. So let me use the calculator. Yeah, so that gives you 1.25. So that's 1.25 times the value of c times, what is the value of t? It is the time taken with respect to the Earth observer, which has already been calculated above. Or we can directly take the value of CT. Instead of writing C and T separately, we can take the value of CT directly. So what is the value of CT of the light reaching the spacecraft, which is 5 kilometers. So I'm going to plug in the value of 5 kilometer directly there instead of making C separately or T separately. So that's 5 kilometer minus, what's the value of V? The speed of the spacecraft, that is calculated as 0.6 c in the first bit, times the distance. From the graph, we know it traveled a distance of 3 kilometers from the Earth frame. So that's 3 kilometer divided by the value of C. The C gets cancelled. And if you simplify this, the value of CT prime will be 4 kilometer. The space-time diagram shows the axis of inertial reference frame S and the axis of second inertial reference frame S prime that moves related to S with speed this much. So value of V is given, which can help you to find the value of gamma. Let us calculate and keep it ready. So that is gamma equals 1 by root over of 1 minus V square over C square. So plug in the value of V as 0.745 C will give you the value of gamma to be about 1.5. Next, event E has a coordinate x equals to 1, CT is equals to 0. So this is the event E here, and its coordinate is given here. Show that in frame S prime, the space coordinate and the time coordinate is this. So this is the value of x prime, and CT prime is what you have to show. So I'm going to use our Lorentz transformation, that is x prime equals gamma times x minus vt. The value of gamma is being calculated 1.5. The value of x is 1 minus v, which is 0.745 c times the value of t is 0. So that gives you is 1.5 meters. Next, CT prime, which is given by CT prime equals gamma times CT minus Vx over C. So gamma is again 1.5. The value as CT is 0 minus the value V 0.745 C times X 1 over C. Substituting this and calculating will give you negative 1.1 meter. Next, label on the diagram the space coordinate underline. When they say space coordinate means on the x prime frame. Label this event with letter P. So I wanted to locate this event E on x prime, which is my x-axis of S prime. I've drawn a parallel line to my y-axis of S prime. So I'm going to draw a parallel line to my y-axis, right? As you can see, this line and this line is parallel, and the point where the line intersect my x prime frame is my coordinate P should be labeled. Next. Label on the diagram the event that has a coordinate x prime equals 1 meter and ct prime equals 0 meter. Label this event with the letter Q. Now, so we know that the P is representing a space value as 1.5 meter, and we wanted x prime to be 1.0 meter. So what we're going to do is we're going to take a ruler and measure the length. How much is this length in centimeter, which is representing 1.5 meter? Then we'll see how much length is required for 1 meter. Okay, so before that, let me use a protractor to see how much angle is it making approximately. It is making an angle of about 36 degrees, right? So let me set this ruler to an angle 36 degrees and measure the length. So P is about 7. Right? So 7 centimeter is representing 1.5 meter. Then 1 centimeter would represent 1.5 meter by 7. But the question is not 1 centimeter length of the ruler, but 1 meter on space. So if 1.5 meter is 7 centimeter as per the ruler length, then 1 meter on x-axis will be how much centimeter? We'll do unitary method, which is 7 divided by 1.5, which gives you about 4.7. So we'll see where is 4.7 centimeter. That's over there, right? So let me keep the ruler a little bit aside. Yeah, so that's the point over here. And we'll label that as Q, which is representing the x coordinate as 1 meter. Okay, representing x coordinate as 1 meter. Next. A rod at rest in frame S has a proper length of 1 meter, proper length L naught 1 meter. At time t0, the left hand end of the rod is at x is equal to 0. So that's the left end of the rod. And the right hand end is at 1 meter. So that's the right end. And that's your rod. Okay. The rod is resting on this line. Now, using the space-time diagram outlined without calculation, y observer in frame S prime measures the length of the rod to be less than 1 meter. Now, first of all, the observer who is in space or the observer who is moving. So, with respect to the moving observer, because he cannot measure the proper length, since he is moving with a speed close to the speed of light, he will end up, seeing the shorter length. But yes, he will make sure that he measures both the ends of the rod at the same time, right? I mean, because since he is moving, he cannot measure the first end and the last end at a different time interval since he's moving away. So he has to measure both ends of the rod at the same time. Now, keeping this in mind, that he has to measure both ends of the rod at the same time, that means if he is measuring the first end at this CT time period, he has to measure the other at the same CT time period. If you're measuring at this CT time period, one end of the rod, he has to measure the other end at the same time period. If you measure the first end at this CT time period, the other end has to measure at the same CT time period. That means if you see the possible coordinates is going to be giving you a word line, right? It is going to give you a word line which is going to be perpendicular to your uh, time axis, right? Now, the intersection point, this parallel line, this vertical line that you've drawn from the event E, the point where it intersects the x prime axis is where you are going to get the other end because initial length is obviously at the origin. The other end will be the point of intersection. Now, as you can see, the 1 meter is at Q. right? The 1 meter as per the x prime length is at Q, but the ends of the rod is shorter than the 1 meter. And therefore, from the space-time diagram, we can say that yes, the length of the rod is shorter than the 1 meter. Next question. Using the space-time diagram, estimate the length of the rod in S prime frame. So you have to just find out this length. Let me label this as AB. You have to find this length AB. So I'm going to take the ruler. The same thing you will do it in the exam, right? So I remember it was 36 degrees. Yeah. And we'll measure what is the length of that AB, which is about 3.3 centimeter as per the ruler. So yeah. So that length of the rod as per the S prime is 3.3 centimeter. But since we know that 1 centimeter is equal to 1.5 meter divided by 7, then 3.3 centimeter will be 1.5 meter divided by 7 times 3.3. So if you solve this, you're going to get about 0.76 meter as the length of that rod.